Hi, I am CH Vijayakumar, working as assistant professor in the Department of CSE, AML and IoT. Today, I am planning to give a small lecture on reinforcement learning, and it's all about MDP, Markov decision processes. It's a part of reinforcement learning basically. So, I'm going to give a small brief on MDP processes, how exactly the actions taken and how exactly the reward functions will work on this based on MDP processes. So let's have introduction. Reinforcement learning is about learning by interacting with an environment to achieve a goal. And basically, an agent learns from consequences, rewards, or penalties. So here we will always we will call the consequence as rewards and penalties. So basically, in RL, we often model problems using Markov decision processes (MDPs). So basically, an MDP is a mathematical way to describe a decision making where outcomes are a partly random and a partly under the control of a decision maker. So finite Markov decision process (MDP). So what do you mean by a finite MDP means? There is a finite set of states S and a finite set of actions A. The next state depends on only on the current state and action, that is called a Markov property. So once the actions and the set of states defined, so rewards are given for each action. So formally, a MDP is defined as S, capital S, a set of states, capital A set of actions, P of S prime such that S comma A. So that means probability of moving to state prime, state S hyphen, that is called S prime, from state S after action A. So that is what state transition probability, a probability of S prime given S and A. Here S is a current state and A is an action. S prime is going to be a next state actually based on that action. So the probability of reaching state S prime given that we are in state S and taking an action A. For example, let's talk about self-driving cars. So P of at intersection and approaching comma go straight equal to 0.8. Here 0.8 means 80% of the chance to reach that next level, to reach the next state. So here our current state is approaching. We are at approaching actually. So our action is go straight. It is directing that if you go straight up to 0.8 miles, so you will reach an intersection. You will reach a junction actually. So that is what here the probability of at intersection approaching comma go straight equal to 0.8. So there is 80% of the chance you will reach the intersection if you go straight from your current location. Now let's talk about rewards receiving when moving from state to state. R of S comma A comma S prime, that means a reward received when moving from state S to S prime via action A. Reward function. So basically a reward of S comma A comma S prime, the reward for taking an action A in the state S and ending up in the state S prime. For example, let's talk about robot vacuum cleaner. R of living room dirty, clean, living room clean. So let's talk about how much the rewards we are getting, the robot is going to get it. So here the reward function, like the first parameter is like living room dirty. So the task is like living room dirty. Now the present status is living room clean and this clean. So if you apply, the action is clean, the present state is living room clean. Now the next prime state is living room clean actually. So living room dirty is now the present state, clean is the action. So living room clean is going to be the outcome of the particular this action. So this is what here, how much reward we are going to get it. That is the question. So here, as we mentioned, it's a +5. So that means living room is dirty. So once it is cleaned, so living room will be clean actually. So living room clean, the state will change to living room clean. So that means it is getting the agent is getting a +5 reward points. So means the robot earn +5 points when it successfully cleans the living room. So here gamma is a discount factor. It's a importance for future rewards. So let's talk about a small definition about gamma. A number between 0 and 1 that determines how much the agent value future rewards compared to immediate rewards. So gamma is always expecting the future rewards, not immediate rewards. So for example, say a small interpretation, gamma close to 0, that means the agent focuses almost entirely on immediate rewards, not a future rewards. But whereas if gamma is close to 1, agent values long-term rewards. That is means it's a far-sighted bit. If it is close to 0, it's a short-sighted. If it is close to 1, it's a far-sighted. For example, students studying for exams, gamma equal to 0.1. If I take the discount factor as 0.1, student chooses to watch TV now, ignoring that exam. So that means he is not expecting any long-term rewards. So if it is discount rate gamma 0.95, the student studies now, but not expecting immediate rewards, but aiming for a good grade later on. So that is the implementation of discount factor in our reward functions. An agent environment interface. So think of RL as a continuous loop between two main entities. One is agent and another one is environment. The learner, a decision maker, choosing that actions, and environment, the system, the agent interacts with, responds with a new state and reward. So what is that interaction process actually at time time step T? The step 1, agent observes state ST. The second step, agent chooses an action AT. Environment, now environment is responding, environment responds, move to the next state, that is ST plus 1, provides reward by providing reward RT plus 1. So whenever you change the state from current state to next state, obviously you will get a reward. Either it can be a plus or minus. It can be a penalty or it can be a bonus point. So let's see a small diagram, agent environment loop. Here you can see an agent starts with a state ST. So ST is my current state and it is interacting with the environment. So once it is interacted with environment, so from environment I'm receiving a reward at the same time the next state. That is what ST plus 1. So RT plus 1 plus ST plus 1. Again it will go to that. That will be a return value for agent actually. So from again the loop continues like RT plus 1 and ST plus 1. Now again the environment will give RT plus 2 and ST plus 2. So it continues till the action completes. So an example, for example, imagine a robot vacuum cleaner. Here agent is robot's control system. That is application maybe you can say. An environment, the house, rooms, obstacles and dirtiness, etc., etc. And the state, current location, plus cleanliness level of area. And now action, move forward, turn left, turn right and start cleaning. These are the actions actually we are expecting from a robot. So based on that action, generally we will get that rewards like plus 1 for cleaning dirt. If it is cleaning, it's okay. We have given some instructions to the robot and it has to go to there and he has to clean that particular wall or particular floor. So once it is followed that instructions, once it is cleaned, so agent will get plus 1. So in this process, in this connection, if robot is hitting a walls, is going forward and moving forward, and it is hitting some walls and it is hitting some other obstacles, then obviously the reward point is going to be minus 1. So it is going to be like that actually. So this is the best example for agent environment interaction. Goals in reinforcement learning. The main goal is achieving a maximum cumulative reward over a time. The agent is not just reacting, it is planning actions to get the highest total reward. This is often represented as maximizing the return actually. Let's talk about a small equation, GT equal to RT plus 1 plus gamma, where gamma is a discount factor, RT plus 2 plus gamma square RT plus T, so on like that. Where gamma lies between 0 and 1. 0 less than or equal to gamma less than or equal to 1 is the discount factor actually. Why close to 0? Agent focuses on immediate rewards. If gamma closes to 0, it focuses on immediate rewards. If gamma close to 1, agent cares about long-term rewards. We already discussed about a real life example. A student preparing for exams, immediate reward, for example, student is not bothering about immediate one, so he just watching a movie or instead of studying, so it's a short-term happiness, so that is what an immediate reward. So long-term rewards, studying consistently and getting a high grade, so that means the student is expecting long-term rewards. That means in the first initial case, immediate rewards, so gamma should be close to 0. Whereas if it is expecting long-term rewards, gamma should be close to 1. Let's talk about rewards. Reward, feedback from the environment about the last action. Rewards guide learning, not instructions. Generally, rewards always guide learning, not instruction, not giving any instructions. Just signals of like good and bad outcomes. The agent's objective is not to find the shortest path or fastest completion. It's to find the strategy that maximizes total rewards. For example, self-driving car, example, plus 10 for reaching destination safely, minus 5 for sudden braking, and if it is a minus 100, it's a penalty, rewards for accidents, plus 1 for obeying a traffic signals. So it built on like that actually. The reward functions are built on as per our self-driving car. Yeah, let's put all together. For example, let's take another scenario. Online food delivery app. Here, agent is going to be a delivery app's AI, and environment is going to be the real world. Like we are interacting with that environment. Like we want to order a food actually through our agent app. That is what. For example, I have that same app in my mobile phone. So that is going to be my agent actually. So environment means the real world, the restaurants I'm interacting with, the delivery partners, and the traffic congestion, etc., etc. For example, the state. The state here we can mention that location of the restaurant and traffic conditions and delivery partner availability, etc. And action is going to be like assigning a partner A, B, or C, or any other agent. Choose the fastest route. So these are all called actions. Choosing a particular fastest route and assigning some partners to my food order app to deliver that. So that is what the action. So reward is going to be plus 5. If I'll get a plus 5 reward points once it is on-time delivery. If it is a plus 10, it is a early delivery. If it is minus 10 for late delivery. So these are the reward kind of things happens in our food delivery app. So here the goal is maximizing a customer satisfaction. That is high total rewards over a particular time. That's about a simple scenario of actions and environment and rewards with a sample application called online food delivery app. Key takeaways from this Markov decision processes session. Finite FDP is the backbone of oral problems with a clear mathematical structure. The agent environment loop is central. Actions lead to new states and rewards. Goals are defined by maximizing cumulative rewards, not just a single step gains. So rewards are the only guidance an agent gets. They shape the agent's behavior. Right. So this is all about Markov decision process. And this mostly this is the part of actually reinforcement learning. So is a professional elective which we are having it in a for final year AML students. So that's all about MDP process, MDP session. Thank you. Thanks a lot.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.